またユーザーで言うとか、ユーザーのマシンとか。
Now, researchers have found a new method to speed up positrons. Instead of using two bunches, they found that this bunch interacts with the plasma in a way that the bunch head creates a wake field that is accelerating and focusing for the bunch tail. Plasma wake fields, especially neutrons and positrons, can be used one day to build collider structures that are 100 to 1,000 times shorter than current designs. Even before then, they could potentially be used as a small-scale add-on to existing or future linear accelerators, boosting their energy and collision power.
Alright, so you may be asking, like, what? Yes, we make antimatter. Like, we do it all the time. Now, truth be told, the beams of antimatter we make are incredibly special, and we'll talk about that in a second. But to give you some perspective, we're not powering the Starship Enterprise just yet. You know, the total amount of antimatter we've made in the history of the is a grain of salt. So it's not a lot in terms of physical stuff, but it's got a tremendous amount of power, and it's going to allow us to do a lot of neat experiments. So anyway, you may be wondering, how do we do this? So here's a sort of a cartoon or a schematic of what the accelerator looks like, all the individual pieces for the first 2 kilometers that we cut. So there's an electron source, which is out west near where the lab intersects Whiskey Hill and Portola Road. And then the accelerator, the beam, gets progressively built up energy and is compressed and made short and then focused and made small in all the dimensions and then eventually sent into the plasma 2 kilometers long later. Well, it turns out, after the beam's gained almost all of its energy, we have the option to fire a very fast deflecting magnet and kick the beam over into this beam line here. And we can send some electrons into this beam line, and then we hit a very dense target, a target that's made out of tungsten and rhenium. These are very heavy, dense materials. And what happens is as the particle beam hits that material, it starts to slow down and emits a special kind of radiation, Remstrom. And it gives off a lot of energy very quickly. And the energy it gives off is in the form of photons. In this case, a lot of gamma rays. And these gamma rays, other particles like electrons.
もしかしてまだ
Then we use different magnets.
無料バス取ってるからね。
We collect only the positrons.
取ってないから。
Give them a little bit of energy, then put them in a beam line, which is actually up in the ceiling of the accelerator down the tunnel. Bring them all the way back 2 kilometers upstream, re-inject them. Actually, drop them down.
一本水があるはずなんだよね。源。ああ。さすがにないな。一本杉スキー場、この間行ったやつだ。ゆべし。 T のスイッチ。
the narrow divergence of the beam, when we looked at how hard the beam was defocusing coming out of the plasma, it was not defocusing very much at all. And also it didn't have this halo around it. We were expecting to see this cloud of defocused electrons around the outside. And we didn't see that. And this was completely unanticipated. And as we, redid the experiment,
一本過ぎどうなってんのかな。
we finally settled in on what was actually happening. So instead of and then they all flow outwards after the fact, and we get these defocusing forces or non-uniform focusing forces. Instead, what started to happen is that some of the plasma electrons would indeed flow right through the beam and continue on out and then come back sometime later. But some of the plasma electrons would actually stay on the axis. They were mutually attracted to the positron beam.
湯沢高原まだ
Just enough plasma electrons
まだやってる。
propagate with the incoming
今度だ。
positron beam, so that now the forces, the positron beam by itself would like to naturally defocus. Plasma electrons don't make it focus, and so it turns out you get these two things would settle into an equilibrium state where they would propagate in a condition where they didn't want to defocus.
この草を冬の間どうしてたのかな。
In addition, the
ほら草ボーボーじゃないですか。 草ボーボーなんやここ。
So, again, it's one of the nice reasons why we do experiments and we study things, because this was not predicted before we started to do the experiment. But we've answered a lot of interesting things with FAST.
ここで
A
なん
lot of
か
questions we'd still like to understand
こんな感じやの
about
人
plasma
の話
acceleration
だっ
going
て。
forward in the future. And now we have another issue. So much like before where we had to pick up our stuff and get out of the way LCLS-1, now we have to do the same things. We have to get out of the way LCLS-2.
夏は草ボーボーなんや。
The facility that uses the first 2 kilometers of the LINAC, we're actually going to have our final runs turn off in April of next year. And that's because the laboratory has this fantastic new project called the LCLS-2 coming along. So what's going to happen is, after we turn off in April, we're going to go through and take out anything that's useful and can be salvaged in the first kilometer of the LINAC.
田んぼ
All the accelerator structures, magnets, anything that's useful, we're going to take out of the LINAC. And then it's going to be put in a state
これ綺麗にかぶるんですけど
contractors
ね。
can come in, cut up what's left, clear the whole thing out, and they're going to take it down to the walls, so that literally the only thing left is probably going to be the light fixtures. So they're going to clean out the first kilometer of the LINAC and put in this fantastic new superconducting LINAC. And why that's so wonderful is because the existing 50-year-old LINAC has, got us several Nobel Prizes. It served the LCLS, FACET, and a multitude of programs and done fantastic work for us. But it delivers electron beams at a rate of about 100 times per second.
農家です
The new accelerator we're going to put in the front
畑
part
じゃ
of
ない
the
です
LINAC
か
is
これ。
going to deliver electrons at a rate of 1,000,000 times per second. So that's going to change what we can do with
なるほどね。
and make X-rays downstream.
どっちが本職かわからない。
As we do that and get ready to upgrade the first kilometer of the LINAC to help us answer the next set of questions that we want to answer for plasma wake field acceleration, we're going to build a new facility called FACET 2. So what that's going to look like is we're going to still leave all of our equipment, the plasma source, all of our instrumentation, we're going to leave in the middle kilometer of the LINAC here out at Sector 20.
布場行ってみました。布場。
Looks like each kilometer of the LINAC. We're going to add a new electron source, and that's going to give us new beams that have new properties, let us answer a new set of questions, and that'll be the first phase of FACET 2. Second phase, we're going to add a new damping ring inside the LINAC tunnel to allow us to get positrons going again. And then the third thing, which is really cool, is we're going to add the capability called a sailboat chicane. This is a special beamline that will let us deliver electrons and positrons to the plasma at the same time, so we can do a whole bunch of cool questions with that. And this is the time frame. This is all going to happen over roughly the next 5 years at the lab. So the accelerator that you see now is going to look completely different about 5 years from now.
あら、できてる。
Now, in thinking about, well, we've done a lot of nice work for plasmas, what would be the next set of questions that we would want to answer with plasmas? I guess, every once in a while we step back and we think, all right, if we just had our way, how could we, in the far future, how could we do something really fantastic and maybe put a bunch of these plasma accelerators together to make a tool for high energy physics? And this was the latest concept of how we thought we might do that. We developed this for something that's called the SNOMAS process, where every 5 to 10 years the physics community gets together, thinks big thoughts, and tries to give recommendations to the government about what are the big projects we should do in the future. So as part of that process, we thought to ourselves, all right, what would a collider look like if you made it out of plasmas? And basically what it looks like is a bunch of little plasma cells where each time one of these plasma cells gives about 25 GeV of energy to the beam. And you do that many, many times, and so you get 25, 50, 75, 100. And after about 20 plasma stages, you very rapidly have very high energies that you can use for a collider. And then you power each of those stages with an independent bunch of electrons, which you then create and distribute accordingly. So with facet 2, we want to answer not only how do we make one individual one of these plasma accelerator stages, answer the rest of the questions for that, but then think about how can we string them together and do it in a way that's compelling, both because we want to accelerate electrons and we want to accelerate positrons. So one of the things that I told you, we discovered this new regime for accelerating positrons where we actually drive the plasma wake with a positron beam. That's very interesting, but it turns out from that picture I showed you before, it'd actually be electrically more efficient if we could actually set up the plasma wave with a beam of electrons and then sample it and accelerate a beam of positrons behind it. Well, to do that, we now have to get around this issue of the defocusing fields from the positrons. So one of the ways we're looking at doing that is creating a special kind of plasma structure where the plasma is not uniform. It's called a hollow channel plasma. And this is actually, the early work on this is being done by one of our PhD students, Spencer Gessner, who's in the audience somewhere. And what it looks like is you can now imagine that instead of making a uniform plasma where the plasma electron density is the same everywhere, they use a special optic which changes our laser pulse so it only makes a plasma which has a special annular shape, and now the beam comes down the middle of the tube here. So essentially the plasma looks like a straw. There's plasma electrons on the outside and no plasma down the middle. So the beam can propagate down the middle of this, and as it does, all these plasma electrons which are out here in the perimeter, they're going to oscillate back and forth. And that's going to give me accelerating fields that I can use to change the beam energy very rapidly. But because there are no plasma electrons inside the middle here, I get no focusing forces. So in principle, I can now send an electron beam through this plasma, get very large accelerating field, but not have to worry about these defocusing fields from the plasma electrons. So we're doing some of the early work to develop this sort of plasma source right now, but looking ahead to facet 2, we actually want to now do this for real and show that we can send an electron beam through, excite the plasma wake, and then send a positron beam close behind it, boost the positron beam with a very rapid accelerating speed. The second thing we'd like to do is stages together. So one of the things we'd like to answer is, okay, how accurately do I have to control how I position these two bunches next to each other in terms of how closely they're spaced in time, how accurately I align them together, left, right, up, down. So to do that, we're actually going to add an independent injector so that we can send one beam from the accelerator, drive the plasma wake, and then use a different electron source and understand and characterize and make these measurements about just how precisely I have to position the beams with respect to each other. The second thing we'd like to do is take advantage of the fact that accelerator physicists are very creative, that most of the beams we make in the pipe, if you were to look at their profiles, it looks like a bell curve, the same distribution you get when you plot grades in a classroom or something. But it turns out we actually know how to make beam distributions where it's not just a Gaussian or a bell curve. It actually has a different shape. And it turns out you can optimize what you get in the plasma so that you get an energy boost which is much larger than this factor of 2. We can do a lot more than just doubling the energy each time we go into the plasma stage. We can get an energy gain 5 or 10 times the initial energy. So these are things we want to look at by taking advantage of the fact that it's so much. The final thing, not just using plasmas as accelerators, but typically using plasmas as reagents to make the electrons together. So one of the things that the X-ray laser or the LCLS we have work is the fact that people developed this enabling technology called a photoinjector. And what's so important about the photoinjector is it makes a distribution of electrons that have a very good beam quality. And what I mean by beam quality is the focusability of the electrons. It means if you ask them to do something or move in a certain way, they all are going to move at the same way. And by doing that, when the beams have this exquisite quality, you can get devices like the X-ray laser that work very well. Well, the source for this, these electrons is actually fairly simple to understand. Picture of a variant of it. And the way that works is imagine that I have an accelerating structure here is I send in high power microwaves, and those microwaves make these very laser beams. Flying out the back end of this very quick. Now the beam size when it starts off in this accelerator, until we get the beams too tightly, otherwise they push each other.
非寄りと
So the beam starts off with sizes when you
しかも 伊沢スキーハウスこの間行ったとこだ。もっとだ、もっとこっちだ。伊沢高原ロープウェイまだやってますね。まあ1000円でしょ。この間と同じとこか。
Sarcoplasmatic reticulum. Right. So these finals is what's called the equilibrium of the homeostatic level and calcium at this rate. And of course, we you change when you put a drop something similar. They happen and you reach a steady state. Here,
運動バゲレンね。これ目の前でいいんだけど。あ、冬はこんなになるんや。あ、夏は。あそこずっと登っていったんやけどな。どこさ。これもう深のこれに全部雪が覆いかぶさるんだ。これ切るんですかね。そのまま圧接するんです。
We claim here that actually you don't understand almost anything. I mean,
なるほどね。これがスキー場の夏なんだね。いいんやら悪いんやら自然のままです。いいっちゃいいけど。ここ駅の前でよかったんですけどね。一緒に駅。はあ、疲れる。探索にあれだけ雪が積もってたのにもう全くなくなる。
Here. Okay, useful for understanding submarines because, as Eisner showed,
トラバス。あ、ゴンドラが動いてます。はあ、観光にするとすると何ですかね。草刈ればいいの。そりゃそうだ。酸素、大峰酸素。はあ
static level. So bear with me the nomenclature.
Maar die hele studie behandelt dat
Sure. I'm going to call the oil count that goes into the stack via any kind of electricity channel. You know just CL. Okay? If I integrate all that during 1 bit, because again, I'm kind of
感じは熱っ。
calcium comes in.
熱いってことはなんだろう。これで100円浮いた。熱いお湯でしたね。熱い。消毒してあるかもしれない。知らん。はあはあはあ。
Now we're going to show mainly in this talk how we have a taste. Now the plane is under linear conditions and all.
これやばい。
And after glass salt, luckily. We cannot make any claim about atria, right? In the ventricle, if the pacing is not too fast, so if you don't go up to 3-4 hertz, right, more than 4 hertz,
どうもすいません。
the pacing is way larger, the time scale is larger than any recovery of the receptor, any
ああ、足湯あるな。
the thousand of changes and interactions and variables if you make a model that you have, right? You can say that these changes of these currents or these changes of calcium
これ全部してみよう。
just have a cell. Once you have the pacing, or there is no calcium that So our claim is that actually once you have set a specific cell with a specific formulation, specific way of working, these currents, these changes in ions only depend on the precistolic values, or mainly depend only the precistolic values of the total calcium. Right? We have to check that that claim is right. Okay? But if it's right, then I hope that you believe immediately that you can make a very nice and easy map. Right? If you have the total amount of calcium at the first speed,